lot of it yesterday, actually more than I anticipated. So what we have left is really just talking about domains. So we're going to wrap up this. I'll give you a little bit of time to work on homework, and if everybody's starting to wind down and get done, then we could even start the next section so that you don't have any homework over the weekend, okay? The next one is pretty short. It's like 3 whole examples, so we might do one of the 3 today. When I'm talking about domain, so that's something we did a lot last year. There's really 3 instances you have to worry about. We need to worry about fractions, radicals, and logs. If it's not one of those 3 things, chances are your domain is everything. How do we write it if it's everything? Negative infinity to positive infinity. Nobody said all real numbers. You just made me so happy. You remembered. You like infinities now. So, if we have a fraction, what do we have to worry about in a fraction? The denominator. So the bottom of the fraction cannot equal 0. Whatever makes the bottom 0 gets taken out of our domain. All right, with a radical, not all radicals are a problem. Which ones do we have to worry about? Okay. Do I have to worry about square roots? Can you do the square root of every possible number? No. What happens if I give you the square root of -4? It's imaginary. Okay. Can you do the cube root of negatives? Yes. So if it's even roots, so square root, 4th root, 6th root, and so on, the radicand, just for clarification, that means the thing, oh, okay, like crazy. So the radicand is the thing under the radical. Has to be greater than or equal to 0. If you have negatives under a radical in an even root, you would get an imaginary. All right, and in logs, that's probably one we are least familiar with, just because we only did them at the very end of college algebra. It wasn't something we saw all semester long. We didn't use them at all in trig. But in a logarithm, the argument, the thing you're taking the log of, must be greater than 0. We can't do logs of 0 or a negative number. And when we get to anything involving logs, we'll talk more about that. But those were the 3 instances where we've had domain issues in the past. When I'm asking you to find the domain of a function, then we have to start out assuming it can be anything, and then look, is there anything we have to take out of this domain? So I've got a bunch of those for us to practice. A, if I have the square root of x plus 2, it's an even root because it's a square root. So what do we have to worry about in the radical? The radicand, so that's the thing under the radical, which is just x plus 2, has to be, so that tells me x has to be greater than or equal to -2. So my domain, what can x be? Infinity. Bracket on the -2, parenthesis on the infinity. Have a fraction. In a fraction, what do we have to watch out for? The denominator cannot equal 0. What do I need to do to figure out what makes this 0? We can plug in numbers and see. We could also essentially treat it like it's equal to 0 and solve. What can you take out of this?
X.
So if I take out x, we're left with, okay. That can't be 0, so can you tell me what x cannot be? Positive 1 or 0. Because you have to look at both of those. So what would make a plain x equal 0? Just a 0. What would make x minus 1 equal 0? A positive 1. You guys see where I got those? Our general rule last year, I wanted an implementation, but I told you if there was more than one value x could not equal, I would allow you to just list it. So if it's only one thing, go ahead and write it as an interval. If it's more than one, you can leave it in a list like this. The interval notation for that would look like this. It would be negative infinity to 0, union, so we have everything smaller than 0, everything between 0 and 1, union, everything bigger than 1. But on that problem, I would take either of those. Okay. C. Do I have a fraction? No. Do I have a square root? Do I have a log? No. So what's my domain? If it doesn't have anything that violates a rule, it could be anything. All right. D. We have a few things here. So let's start here. This 3 over x. What do you know about that? It's a fraction. So the bottom cannot be 0. Okay, then I have a cube root. Do we have to worry about cube roots? No. Odd roots can be anything. So the only thing I have is x cannot equal 0. So how would I write that? We have a fraction. We know in a fraction, the denominator cannot be 0. So what do we have to do? What do I need to do with the x squared plus 7x plus 12? Easy method, back to that. So that would break into x plus 4, x plus 3. So x cannot be -4, -3. You can leave it like that. If you chose to write the other, it would be negative infinity to -4, union -4 to -3, union -3 to infinity. And the last one, we have a log. In a log, the argument, the thing you're doing the log of, has to be greater than 0. Do you guys remember what logs represent? It's basically, just as a little side note, if I said like log base 2 of 16, that means to what power equals 16. And so the answer to that would be 4. So the answer to a log is looking for an exponent. The reason this argument has to be positive is the base of a log is always positive, and when you are taking a number to a power, a positive number to a power, you'll always get something bigger than 0. So that's why our argument has to be greater than 0. So 2x plus 5 greater than 0, just solve that inequality. So 2x is greater than negative 5, so x is greater than negative 5 halves. So my answer interval notation would be parentheses negative 5 halves to positive infinity. Is that okay? So I'm going to give you guys some time to finish that handout. Towards the end of the class, I'll probably start the next section just because we'll have time, and then that way you'll have time to do tomorrow's homework in class and not have to take it home. Okay, I just want to try to maybe get through one of these. There's only a few on here. I did print empty slides beside them, so you have plenty of room to write this time. It's a pretty short section. Just a review on linear functions. So what's a linear function? It's a line. So how do you write the equation of a line? What do you need? Y equals mx plus b. So you need a slope and a y-intercept. Or you can do it if you are given 2 points, right? So that's what we're going to be doing, reading a scenario and writing an equation and answering some questions. So example 1. As dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, express the temperature T in degrees Celsius as a function of the height h in kilometers, assuming that a linear model is appropriate. Okay. A lot of stuff there. It's asking us to write the equation of a line, essentially. Now we do have to be cautious. I told you that I want temperature as a function of height. So that is telling you which one is x and which one is y. You can write the equation either way, but only one way is going to be correct because I specified right here. So temperature is the function. So would that be the x or the y value? Think about f of x, right? Is the y value. So the function is the y value. So in your ordered pairs, I am telling you that the y value is my temperature. So my x value is the height. All right, I've also given you variables to use. So am I asking you to use x and y here? No. I want h for the x and t for the y. So using that, let's get our order pairs. The ground temperature is 20 degrees Celsius. So the temperature is 20. My x value here is my height. If you are on the ground, what is the height? 0. Okay, second order pair. At a height of 1 kilometer, so that would be my x, the temperature is 10. So that is the y. So remember, first you have to find your slope. Change in y over change in x, or y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Does everybody remember doing that? So y sub 2 would be 10 minus y sub 1 is 20 over x sub 2 is 1 minus x sub 1 is 0. So I get negative 10 over 1 or negative 10. Alright, right, looking at this, I actually know the y-intercept already. Anybody tell me what it is? Let's see. If you don't know your y-intercept, what did you do? How did you find it? We now know the slope. You guys remember just plugging it into y equals mx plus b? So what you would do, I don't know why it keeps doing that. That's kind of annoying. Y equals mx plus b. So you take one of your two ordered pairs. Let's say I took this one. What's the y value? Equals my m, which is -10. X is 1 plus b. So we get a y-intercept of 20. How could I have known that before? Yeah, the point was 0, 20. A y-intercept is what's the value when x is 0? So you could have just seen it from that order pair, but if not, we worked it out. It took us 10 seconds. We got it. No big deal. So my equation, I asked for it to be written as a function. Okay, and it was temperature as a function of height here. So instead of x and y, we said we're using h and t. So my y is my t equals my m, which is -10, times my x, which is h, plus 20. So temperature, -10 times the height, plus 20. Part B. What does the slope represent? I am looking for a sentence here. So you did that way back in the day with Mrs. Keller. You were interpreting rates of change. When we found our slope, we did y over x. My y was the temperature, right? So what was my unit for temperature? Did you do okay? Mm-hmm. My x was my height. What was my unit on the height? Kilometers. Okay, and the division we know is like a per. So this is -10 degrees Celsius per kilometer. So now I have to write a sentence. What does the negative tell me? It's decreasing. So the temperature falls or decreases 10 degrees Celsius every 1 kilometer, or just every kilometer, per kilometer, or something like that. So when you interpret your slope, I am expecting you to include the number, so the 10 better be in there, and I'm expecting some units. Don't just tell me it's -10. Okay, what does that -10 mean? Each kilometer we go up, the temperature will fall another 10 degrees. Let's see. What is the temperature at a height of 2.5 kilometers? 2.5 is my height, so we're just plugging that into my equation. Right, -10 times 2.5 plus 20 is -5. And what should I put with that? Temperature will be a -5 degrees Celsius. Do you guys want to do the next one?
Yep.
Let's go for it. We'll do one more. I promise this will be my last one today. So Jason leaves Detroit at 2 p.m. and drives at a constant speed. He passes Ann Arbor, 40 miles from Detroit, at 2:50 p.m. Part A, express the distance traveled in terms of time elapsed. All right, the hardest part on this is figuring out what X and Y are. So the distance traveled would be my Y. My X would be the time. Did I give you certain letters to use this time? No. So you are welcome to, if you want to use T and D, we can. If you just want to use X and Y, we can. Do you guys have a preference?
T and D. What time must be X?
So typically, yes. Now it would be possible, depending on the scenario. I could give you a scenario as long as the Y distance couldn't be repeated. So if you were only moving one direction, we could do it the other way, but typically, yes, it would be X. You want to do T and D? Yeah. Time and distance? Mm-hmm. Okay. So, to write the equation, we need ordered pairs. So the first one, we're talking about time elapsed. So I don't actually want to use like 2 o'clock in there. That's our starting point. So that would be a time of 0. What was our distance? How far have we traveled at the beginning? Is it?
0.
Yeah, at 2 o'clock we started. We haven't left home yet. So at time 0, our distance traveled is 0. All right. Then at 2:50, so how much time has passed? 50, so we're measuring that in minutes, and my distance traveled then would be 40 miles. All right, so slope. Y2 minus Y1 over X2 minus X1. So we get 40 over 50 or 4 over 5. Y-intercept, can you tell me what it is? It's 0 here. So my equation, my Y, which we said we're going to use D for distance, equals M, 4/5, times my X, which was a T, plus 0. So distance is just 4/5 times time. B, interpret the slope. So go back to when we found slope. The top, the numerator, was my Y. Y was the distance. What was our distance measured in? Miles. Okay, the denominator was my X, or my time. And what were we measuring time in? Minutes. So this is 4/5 miles per minute. So tell me a sentence I could use. Okay, so Jason traveled 4 miles every 5 minutes. In 5 minutes, he goes the distance of 4 miles. Something along those lines. You have to include the number and the units. And C. If he continues to drive at the same speed, how far will he have driven by 3:15 p.m.? What is my time at 3:15? 75. It's been 75 minutes since we started. So we're going to plug that in. So let's see. 5 goes into 75. 15 times 4 times 15 is 60, and we were measuring it in miles. So people have traveled 60 miles.